We have the water, the wind. Oh, the sun path, yeah. Sun path on. And if it's too big, we can always reduce the size of the sun path. And if we select this on June the 21st, and we take a screenshot with June the 21st or December the 21st, and this is the difference between winter and summer, okay, in terms of sun path. So with this, we have the sun, we have the wind, we have the natural trees, we have artificial elements that we have created. So I think that's a good summary of this site plan. What else we can do? The pond, okay. Now we have to make it, or we have to understand the potential of this water mass that we have here. That works great if we have a small neighborhood. Okay, we're not talking about a big city or whatever, but if we have a few or a condo with different houses or different public buildings, a library or a commercial building there, that is always a great strategy. Okay, so if we have buildings around Central Park with a pond here, well, it's something that the neighborhood would appreciate, having a green area, a public green area here. It would be great, but we can use this this central element as a seasonal heating strategy. What is the seasonal heating? Well, seasonal heating means that we can get energy in summer. In summer, we have a lot of energy. We have a lot of sun. We have a lot of heat. The problem is that in summer, we don't want to use that heat. We want to get rid of heat. But what if we could store that energy, that heat in summer, and then we could use it in the winter? That would be great. Yeah, we can do that. So those are the seasonal heating or the seasonal storage strategies. And what is the way we have to store energy? Water. Okay, so somehow we need to heat up a big mass of water, and then that mass of water will keep its temperature during the winter, or at least until January. I'm not when the lake or the pond is frozen, it's not keeping the energy. But for those months in October, November, December, when we are using the heating system, when we start using the heating system, if we had a huge mass of water with a temperature that is closer to the comfort, this is something that we can use. Dimensioning this, it's too complicated. There are complicated equations. We are not going to do that, but at least we need the idea that, especially if we have a neighborhood like this, having a centralized water pump that can be heat storage, it will always work well. Okay, so probably we don't know how to dimension this. We don't know the mass of water that we need to do that, but we need a mass of water, a centralized mass of water. And probably all the solar collectors placed on the roofs of this neighborhood. In summer, we don't need this amount of hot water. So if we connect all the solar collectors to this pond, the temperature of that pond will increase during the summer, and then it will be enough to use this warm temperature in winter. Okay, so that's the concept of heating storage. And as you can see, it always works with small neighborhoods. It doesn't work for a single family house, but if we have a neighborhood and everything, all the buildings are connected to this mass of water. Okay, so that's the strategy that we have here. We have solar heat. We can have a plant of solar collectors, or we can have solar collectors on the roof of the building. So all these solar collectors are connected to a mass of water, and we can heat up this mass of water during the summer. We don't need this heat in the summer, but during the winter, we can make the most of this heat that we have stored there. Okay, so we can use this just as a strategy. So if we are working with this site plan, imagine that we have water collectors in all the south-oriented roofs of all the buildings we have here. So if you can use the pond that you are creating to connect all these solar collectors to that pond, that would be a good strategy for winter. Okay, you don't have to calculate it, but we need to know that if we place solar collectors for domestic hot water in all these buildings, in summer, it's not that we can't use this amount of hot water, it's that it can damage the system, because we can overheat the system because we're not using this hot water. So that's why we need to release this heat to the pond. And then in winter, or at least a few months, or during the first months of the winter, we can use the warm water that we have stored here. Okay, so that's another good reason to create a pond. But it works better if we have like a neighborhood, different buildings or different houses connected to the same pond. So that would be another good strategy when we're defining. And then, if you have the idea, be radical. Don't okay, I did a pond, small one. Now try to make the most of it. Okay, so probably it will be interesting if you connect the artificial pond to the natural pond and you create something unique. This is design. This is not energy efficiency, but be radical. Okay, try to do something nice. Be radical. So that's it. This is what we need. First, we have to work with the plants. Well, we're not talking about this, basically, because I'm not an expert. If I were, we would talk about the plants that you can use in every location, but make sure that you work within your work team. You have someone who is an expert on these kind of things, because it gives you points in this kind of standards. Second, we need water. The water, the only condition is that we have contour lines, and it has to be at the bottom of these contour lines. So that contour lines are sloping down, and at the end of this slope, we collect that water. So that's perfect, because we can control floods, and so we can use this pond for a lot of things. Okay, so make sure that we have this. Second, control everything: the sun paths in winter and summer, and the wind in winter and summer, and use natural and artificial elements to protect the building from the wind in winter, or to expose the building to the wind in summer. And then, if you have a neighborhood, if you have some buildings that it doesn't mean that they belong to the same owner, but if there's a relationship between the owners of all these buildings, make sure that you have like a centralized element, a centralized part with a water pond, and connect the solar collectors to the pond. That would be a great strategy to make the most of the site plan. Okay, so if you're working with a site plan, add all these things: the windrows in winter, the windrows in summer, and try to understand the idea that you are using natural elements, existing elements, natural or artificial existing elements, and you are adding something that improves the potential for saving energy of your site. Okay. Now we have to talk about systems, because when we want to save energy, we have design, and in design we include everything. We include the site plan, we include the orientation of the building, we include the shape of the building, materials, thermal insulation, glass. There might be more things. So that depends on architects. Okay, when I'm talking about design, I'm talking about architecture. But then we have mechanical systems. So if we are deciding what kind of mechanical systems we are using, well, basically we have fuel or electricity. So that's the first decision, or both. Okay, we can have fuel and electricity combined in the same building. If we have fuel, nowadays the best fuel is gas, natural gas. Why? Because in terms of CO2 emissions, this is the best fuel that we can use. There are always biofuels. Okay, biofuel. What is a biofuel? It's basically it's burning something that it's natural. There are plants. If we burn oil or we burn directly those plants, we generate CO2 emissions. But we have to take into account the CO2 that this plant has absorbed during its life and the CO2 that it's emitting. So that's why we say that these kind of biofuels are carbon neutral. They are emitting CO2 when we burn it, but at the same time they have been absorbing CO2 during its life. Anyway, biofuels sometimes are controversial because we need a lot of trees, we need a lot of plants, and sometimes if we don't take care of this, we can go further, and we end up using a lot of plants and trees, and we end up damaging the place where we are getting this biofuel. Anyway, that's an option here, the biofuel, but we need to. It's not, oh, biofuel. No, where does it come from? What kind of plants have you used? Are you using a local biofuel, or are you bringing this from the forest in Brazil? I don't know. So we have to think about it. So in terms of fuel, we don't burn coal anymore. I hope we don't burn gasoline or oil or petrol or whatever. No, we are burning natural gas because in terms of CO2 emissions, it's the best fuel. Then we have the geostrategic strategic issues that I'm not going to talk about this. Okay, but in terms of energy, in terms of carbon footprint, those would be the best. A biofuel are the pellets. Okay, so this is biofuel. I'm sure that you're familiar with pellets. Okay, so we have this. Basically, this is wood. It's treated to increase its energy release potential. Okay, but basically it's wood. But this would be a kind of this biofuel. Then we have oil. We have other fuels, but when we are talking about something bio, it's something that comes from plants. We can use fuel boilers, and if we're using natural gas, please use condensing boilers. Okay, condensing boilers are more efficient than the regular boilers. Why? I think I explained that in systems, but anyway, those are the alternatives for the mechanical systems. But the thing for the fuel systems is that we can use this only for heating. If we need cooling, we need electricity. Okay. Is there an alternative? We can use solar collectors. Solar collectors are an alternative to fuel, and it's only for heating. So probably we can move this here. Okay. So in this exercise, I don't have anything against gas. I don't have anything against biofuels, but we are going to try to be carbon neutral in this building we are designing. So we are going to use solar collectors for heating and domestic hot water. This is heating and domestic. Okay. So we are when we are designing the systems, we are going to design systems only with solar collectors and electricity. We are not burning anything in our buildings. If you need to burn anything, let me know, and probably we will agree. But as a rule of thumb, let's use solar collectors for heating and domestic hot water, and let's use electricity for cooling and all the appliances that we have in our building. Okay, everything that runs on electricity. And we have electricity from the grid. Or we have electricity from PV panels. And we have the, well, we are not in the middle of nowhere in any of the buildings that we are designing. So we are not designing a standalone PV system. We assume that we take electricity from the grid, and we generate our own array of PV panels. So when we need energy, we get the electricity from the grid. When we are producing more, we sell that electricity to the grid. Okay, so this is what we are going to do. We're going to work with solar collectors, and we're going to work with PV panels, and we're going to use electricity for the grid, from the grid. If we're working with electricity for cooling and okay, so this is the summary. Now we are going to do this. So we are going to use solar collectors for heating and domestic hot water. And we are going to use electricity for heating and cooling and appliances. What do we need? If I want to use electricity for heating or cooling, what do I need? I need a heat pump. What is the best heat pump that we have available in the market? What defines the the performance of a heat pump? Oh, please, someone. Efficiency, yeah, but what's the concept that evaluates the efficiency of the heat pump?
COP.
COP. The COP stands for
Coefficient of performance.
coefficient of performance. Coefficient of performance. What is it? It's a number that describes the effectiveness or efficiency of heat pumps, refrigerators, or air conditioners. Is a ratio of energy delivered to the hot reservoir to the work input. What does it mean? Yeah, what is the coefficient of performance? We talk about this only in electric systems. We don't talk about the coefficient of performance in fuel systems. We're talking about electric heat pumps. So this is the heat delivered. Well, the heat, let's talk about the energy divided by the electricity, or the electrical energy consumed. Okay. The higher, the better. If the coefficient of performance is 2, that means that if we want to deliver 2 kilowatt hours, the energy that I have to consume, the electric energy that I have to consume is 1 kilowatt hour. And we're going to use this because we're analyzing different things, but we need this number. We need the energy that we want to deliver. Because if we are calculating the electric loads of our building, we have to turn this based on the COP. So 2 well, let's be optimistic. Let's say 2 to 3. It's usual COP from air to air heat pumps. 2 or 3. This concept, again, it's complicated because it depends on the outdoor conditions, the indoor conditions, the system that you're using to deliver that energy. But it's complicated. But air-to-air heat pump, the air-to-air heat pump is the heat pump that, or the system, the HVAC system that we have in our house. We have an exterior unit, we have an interior unit, and we have some pipes running from the outdoor unit and the indoor unit. So this is an air-to-air heat pump. If we are working with water-to-water heat pumps, the coefficient of performance can be up to 5 to 7, depending on the outdoor-indoor conditions. So that means that if we want to produce 2 kilowatt hours, and the coefficient of performance is 5, what is the electric consumption? This one, if the coefficient of performance is 2, and I want to produce 2 kilowatt hours, the electricity is 1. So if the coefficient of performance is 5, and I want to produce 2 kilowatt hours, what is the electricity that I need? 10. The other way around.
Point four.
0.4. It's 2 divided by 5. Okay. Please, we have to understand this before leaving this school or even this world. When we are calculating the heating loads or whatever, what do we get from Revit? From Revit, we get the peak heat load. Peak heat load. Let's say 40,000 watts. Okay, this is a peak heat load. We use this to select the machine itself, because if we read the specifications of the machine, okay, so my machine has 45 watts, 45,000 watts. Perfect, because it's more than 40. And the machine has 20,000 watts. Well, it's not enough. At this peak heat load, when the weather is extremely cold outside, my machine won't be enough to deliver the amount of energy that I need. Okay, so that's why we need the peak load. The concept of peak heating load or peak cooling load, it's important because with this element, we select the machine, the heat pump that we're going to work with. Okay, so now I select select the heat pump. Okay, so first I calculate the peak heating load or the peak cooling load. Second, I select the heat pump. And in the heat pump, I need 2 things. I need the maximum power and I need the COP. Those are the 2 concepts that I need from my heat pump. What's the maximum power? It has to be more than this. Okay, it can be 80,000, but it will be much more expensive. If I only need 40,000, something around 40, 45, 50. Usually this is not 40,000. This is 41,285. So there is not a commercial machine with 41,285 watts. Okay, so what's the next? 45 watts. Okay, 50. Okay, 100. I wouldn't do that because 100 would be too much. Okay, but something between more than 40, between 40 and 50, it will work. So with this, I select the heat pump, and then I select something that meets the maximum power that I need, the peak heating load, and then I need the COP. So imagine that the COP is 4. Okay. Now, if my COP is 4, here I need energy. So how can I turn from power to energy? I need kilowatt hours here. I can do this yearly, monthly, or daily. Let's work with a winter day. Okay, so my peak heat load is 41,285. How many hours is my heating system working? Let's say 10 hours. What's the energy? It's well, 41,000. It's 41.3 kilowatts because we have kilowatt hours here. And what's the energy? 41.3 kilowatts times 10 hours. So that will be 413 kilowatt hour. Okay. Now, what is my COP for? I'm sorry. This is the electricity. And my COP is 4. So what is the electricity that I need? The electric load. My electric load will be 413 kilowatt hours divided by the COP 4. So that is around 103. 103 point something kilowatt hour of electricity. Okay. So that's why units are important. The difference between power and energy is important. With Revit, with the Revit report, we get the peak heating load. With my Excel file, Scott, you have calculated heating loads here. Okay, those are heating loads, those are watts. So you have to add up 6,000, 4,000, 6,666, whatever. So this is the peak thermal heating load that you have in your house. You add up the house that the heat that you lose through the wall, through the roof, through the window, whatever. Okay, so this is the peak heating load. So this is this number, 4,000, whatever. Okay. Now the energy. This is the daily energy. I have decided to do this one day. I can do this 1 month. If I multiply this times 30, I will have the monthly energy. If I multiply this times, well, I can multiply this 346 days because this is the peak heat load. Okay, so that's the energy that I need probably in January. In February, I will need less. In March, even less. In April, hopefully, it will be less. And probably in May or June, I don't need heating, I need cooling. Okay. So that's why at the end, we have this graphic. In January, we have this. In February, we have that. In March, we have this. In April, and then in May, June, July, and August, probably I need cooling load. And then September, October, November, and December. Okay, so this is cooling and this is heating, but this is energy. Okay, so this is the peak load times hours per day times number of days. Okay, if in January I have this peak load, I use my system 10 hours per day, and January has 31 days, so that is the number that we'll have in this part. Okay. But this is the thermal energy. What is the electric energy? I have to use this peak energy load in January, and I have to divide it by the COP of my system. And that's the electric load. Okay, so if we are working with fuel, this is the peak load. Because the fuel, we don't have this option. We don't have the concept of the COP. I burn something, and well, I need to generate that energy. But with the electricity, with the heat pump, we have this concept of the COP. Mechanical engineers are working to increase the COP. 6 is better than 4. 10 will be better than 6. 1,000 will be better than. Okay, we don't know what the limit of these machines is. If the COP would be extremely high, there will be a moment in which we don't need with a solar panel, we can heat up or cool down the whole house. I don't think we will arrive at this point. Okay. When I started studying this, 4 was a great COP. Now 6, we have machines that can get up to 6, but those water to water. And what is a water to water machine? It's a geothermal heat pump. Okay, a geothermal heat pump. It's this. Okay, so it can be a fridge or whatever. It's a box, and we don't know what's inside. But the way it works is like this. Okay, so we have the heat pump at home, and the heat pump is connected to those boreholes. Or it can be vertical, they can be horizontal, or we can use a pond. Okay, so that's why we are using this, because probably this is the most effective way to interchange the heat that we need to take from somewhere. Okay, so a heat pump, it's a device that extracts heat from. In this case, it can extract heat from the air, from the water, and then it can deliver that heat to the house. So that's why we need a pond. And this pond has to be artificial, because we are not allowed to do this in natural ponds. We cannot do this in the Connecticut River or in a lake. So that's why if we do these kind of things, it has to be artificial. So we have to make sure that we're not damaging the fishes or the birds that are using this pond. Okay, it's artificial. I have created this. I'm not damaging anyone. In the event that warming up the water a little end up damaging natural life. I don't know, and I don't want to think about it. But if we are using an artificial pond, we're good. We don't have to worry about anything. Okay, so that's the concept of this geothermal pump. We have to connect the geothermal pump to the pond, but it's not an open loop, it's a closed loop. Okay, so we just release the heat or take the heat from it. In winter, we need to take the heat from that. In summer, we need to release the heat to the pond. So that's what we are doing. And in this case, I recommend you use a heat pump, let's say a geothermal or water to water. Heat pump, because it's more efficient than anything else. And the electricity that we need, this is the electricity that we need, 103, not 413. This is the electricity that we need to get from the PV array. Okay. So when we're talking about electric loads, we have to differentiate between heating and cooling. This is the peak load. Divided by the COP of the heat pump. And then we have appliances. If a computer consumes 200 watts, 200 watts. I don't have to divide this by anything. Okay, but these are the electric loads that I need to, everything that is related to appliances, I mean a lamp, computers, refrigerators, microwaves, whatever. That depends on the time that we are using this. If this lamp consumes 20 watts, it's working for 8 hours. The energy, it's 20 watts times 8. If a microwave consumes 100 watts, but it's working only for 5 minutes, it's 1,000 watts times 5 minutes. That's the energy. So the daily energy depends on the power of the machine and the time that this machine is running. Machine, lamps, computers, whatever. The electric load, first we have to calculate the peak load. We can do this with Revit, or we can do this with the Excel file. We have the peak load in winter, the peak load in summer. Then we have to multiply this by the time in which the system is working. Maybe it's 10, 12 hours in winter, in January. Maybe it's only 5, 6 hours in March. And in May, and maybe it's only 1 hour a day. I don't know, let's see. And then we have the energy. We divide this energy by the COP, and we have the heating and cooling. We have the electric load that we need. So that's the calculation that we have to do. So you should have an idea at least of the peak cooling and heating loads. With this, we can dimension the PV array. For the appliances, again, so what do we have at home? Television, refrigerator, washing machine, whatever. We can, I think in systems, I showed you how to do that. So we can use the same. Where is the system?